Welcome to another video on electronic circuits. In this video, we shall see amplifier parameters. Before we start, let us try to understand some basics. Of course, these are the prerequisites. If you know Ohm's law, KVL, KCL, and BJT amplifiers, so you can easily understand this particular video. Of course, this is what is required. Okay, with these prerequisites, let us start. Now, assume that you have an uh, amplifier. So this is the amplifier as a black box, and let us consider this is the input and this is the output. I think you might have come across this amplifier maybe in so many real life conditions. So let us assume something like this. So let us consider a auditorium like this, where we have so many people sitting over there or listening to some person who is talking. So there is he is holding a mic because he cannot reach so many people, maybe hundreds of people over there. So what we do is we give a mic to that person. He will speak onto this mic. So this voice energy will be converted to electrical energy, and that is passed down to an electronic circuit. It is called as amplifier. So this is amplified. The whatever voltage that is coming out from this mic will be amplified by whatever required amount, and that will be given to the output, which is a loudspeaker. So this is a loudspeaker where you're going to hear his voice loud enough so that all the people can hear to him. So this is what is an amplifier doing. It is actually, suppose if this is the input voltage that is given to the amplifier, it will be amplifying it by AV times. This is what is the input will be passing through AV, so that you will end up with an output voltage V naught, which will be AV times the input voltage. AV times the input voltage. So this input passes through this amplifier having a AV. So this is V in. The moment when it comes out, this becomes V out. So output voltage is gain times the input. Gain times the input. This is what is the thing. Now we know that why we are actually amplifying is because his voice is very low and the amplitude of the signal is low, and we know that voice signal is a AC signal which will be varying around high and low, all those things. So since this is a AC signal which is small in amplitude, need to be amplified. So now this amplifier, which is now represented as a block diagram, we know that it actually has something like this. So this is the input what you have. It is passing through this capacitor. It will be having a biasing resistor, and it will have a BJT over here, and this is the circuit what you have, and you have a VCC connection. This is, we write it as R1, R2, RC, and this is ground, and this output is given to the speaker. Can you see? This is the speaker. You can think of this is the entire setup. Now you have the mic here. I can represent it by a signal, a source, and this will also have some resistance associated with, let us say this as, let us say the input that is reaching the amplifier as V in, whereas the voltage that is generated in the mic as Vs. Let us assume resistance associated with the uh, mic is R signal, and let us assume that this is having an equivalent resistance of some R. Now this AC signal has to reach this amplifier first, and then it needs to be amplified by AV times, and after amplification it should reach the load. You see, now you have a signal having some source impedance. First it should reach the amplifier and then amplified by AV times, and this has to further reach the load. So we can now write how does this AC signal see this entire amplifier as. Now you have a AC signal having some Vs and R signal will see this entire amplifier. It doesn't bother about what is there inside this. It will basically see this as a resistance R in. This is what R in. The input impedance, input resistance of the amplifier. This is what is R in. And we know that this will be this whatever voltage out of Vs, which is minus plus. Okay, let me write it here. This is the black box. This black box is now at the input represented by some R in. This is what is the input voltage V in reaching the amplifier, and I actually have a source of Vs and there is a resistance R signal here, and this is connected to this. And we know that this output, what is coming out, will be plus minus, will be AV times Vin, and this will also have an associated resistance. Let us say it as R out. And finally we have the load, which is RL. The output measured here is V naught. Correct. So what is this amplifier now replaced by? This amplifier is now replaced by R in AV times V in, which is a voltage source, which is plus and minus here, and there is a R. So now we need to know what should be the value of R in and what should be the value of R out. Of course, we already know what is AV of this amplifier from our previous understanding. This was given by the expression minus HFE times RC divided by HIE. So we know what is the expression for AV. Next, what should be this R in? What is the significance of this R in? What is the significance of this R out? So let us assume that you actually have some Vs here. So what is the relation between Vs, V in, R signal and R in? So by writing the KVL here, can I write V in, the output voltage, the input voltage that will reach the amplifier as given by Vs into R in divided by R signal plus I. How did I get this expression is, let me rewrite this. So now let me consider a current of I in. So what is V in? Can I write V in is equal to this current multiplied by R in, I in multiplied by R in, because I know that this is the current what I'm assuming to flow through this. So this input voltage is nothing but the drop across this resistor, so which is nothing but I in into R in. But what is this I in? I in is the entire current flowing through this loop, which is nothing but voltage divided by the overall resistance. Can I write this as Vs divided by R in plus R signal? This is I in into R in. So this is R in, I'm writing as it is. So now can I write this V in as Vs R in divided by Rs plus R in. So this is the expression for the input voltage that is reaching the amplifier upon having some source voltage and having an associate resistance. Now, what should actually happen in ideal cases? The entire source voltage should reach the input. So, what is requirement is V in should be equal to Vs. That means whatever you apply here, entire thing should reach there. So, when that is possible, there are two conditions that is possible when this condition is true. One is R. This is R in. Correct. The overall resistance is R signal plus R in. Now V in is equal to Vs if R signal is 0. If you don't have any resistance here, whatever is the voltage that is there, no drop will happen because of this current, and because there is no resistance, then entire voltage will reach this input voltage. So this means it's an ideal source. Source will always have associated resistance. If it is an ideal source, then R signal becomes 0. then the entire voltage will reach. This is an ideal case which will not exist in real time. So then when does this Vin will be equal to Vs? So there is one more possibility. Even though you have some finite resistance, suppose this is infinite. Suppose if Rin is infinity, you see there is no current itself flowing through this. When there is no current flowing here, this drop is zero. When this drop is zero, so then Vin is equal to Vs. So then Vin is equal to Vs. Again, this is also an ideal condition, because if there is no current flowing through this, then there is no IB, because it won't happen. So now Vn cannot be equal to Vs. If it is equals, it is only an ideal condition. Ideal condition. So what should be the value of Rin so that we get Vin almost equal to Vs? So that is possible when Rin is large enough. Large. So that's why input input impedance of an amplifier should be large so that entire input voltage, so Vs will reach, what is this Vs? Vs is the source voltage. Vs is the source voltage. What is this? This entire voltage will reach here if this is large, so that Vs will reach the input of amplifier with with maximum amplitude. It reaches there with maximum amplitude. So just to give an example, if Vs is 10 millivolt and if our signal is 100 ohm, let us see what happens if R in is also 100 ohm. If Rin is also 100 ohm, then what is Vin is equal to? Is it not 10 milli into 100 divided by 100 plus 100 is 200? Can you see? Are you getting only 5 millivolts? You are getting only 5 millivolts if Rin is equal to R signal, meaning that if the resistance is, because this 100 ohm is a less value, this is less resistance, you can see you are not getting the complete voltage out of 10 millivolt, you are getting only 5 millivolts at the input of the amplifier. Instead of that, if Rin is equal to 10 kilo ohm, if Rin is equal to 10 kilo ohm, what is Vin is equal to? Is it not 10 milli into 10k divided by 10.1k? So now in this case, what will be Vin? So is it not 10 exponential of minus 3 into 10 exponential of 3 divided by 10.1 exponential of 3? Can you see you are getting input as V in is now 9.9 millivolts. The understanding here is when R in was 100 ohm, R signal as 100 ohm, if you apply 10 millivolt, you are getting only 5 millivolt. Suppose if you have R in as 10 kilo ohm, larger value as required here, the input impedance of the amplifier should be large. Now it is large. When it is large, how much input voltage is reaching the amplifier? You can see out of 10 millivolt, 9.9 volt, 9.9 millivolt will reach the amplifier. That means if R in is more and more, then V in is almost equal to Vs. The entire signal voltage, the source of this will reach the amplifier, will reach here if this is more and more. Correct? That's what is the understanding of this. Of course, we can also write here. So can I write V in is equal to Vs minus I in into R signal. So this is another way. If R signal is less, entire thing will reach. Suppose if this is more, can you see R signal is, sorry, I current flowing through this is less. When current flowing through this is less, then Vin is almost equal to Vs, because whatever the value of R signal is, suppose the current itself is less, because when you have larger resistance, the current reduces. This current reduces, overall this is constant. This minus a reduced value will be almost equal to the Vs value, because when you increase this resistance, this will reduce. When this reduces, so amount of reduction of your Vs reaching the amplifier will be less and less. So you will get the complete voltage onto the input of the amplifier. So what is the requirement of the amplifier? R in should be large. Reason, the voltage should read the amplifier input. Next is what should be R out. So we know that it has amplified by some assume that it is increased by 50 times. So 50 times of 10 millivolt is reaching here. So how much will reach the output here? Because you can see when you're connecting RL, some current flows through this. Let us say this is I out. Can we write an expression for the output voltage here? So can I write V out is equal to AV times V in minus of R out into I out. So if this value of R out is more and more, can you see the output voltage is this minus this. So when this is more, will you have the output voltage less and less, because more and more drop is happening here. So when do you get this entire voltage reaching the output? When this drop, when the drop across this resistor is less. When do you expect this drop to be less? When R out is less, when the drop is less, then V out is almost equal to gain times the input voltage. Whatever output voltage you will get here will reach the load if this R out is less. If this R out is less. So there are two. So what should be R out now? R out should be as small as possible. It should be less. If it is less, the entire gain times the input voltage will reach the load. Otherwise, you will have some loss happening over here. So if this loss has to be less, then this should be as small as possible. If this has to get the complete voltage, then this should be as large as possible. So that's why R in should be large and R out should be less for a good amplifier. This is for a good amplifier. This is for a good amplifier. So now let us see another important parameter. So when we actually did the simulation last time, have you noticed that we have used a frequency of, can you just see here, we have used a frequency of 50 kilohertz. Say this. So 50 kilohertz, we had a gain of around 96.5. The question is, does this amplifier, whatever amplifier we thought of, we simulated, does this amplifier has got same gain for all frequencies? So let us see here. Let me change the frequency of this to around uh, okay, 5 kilohertz. Change this to 5 kilohertz and see what happens to the gain. So let me run it here. So now what I'll do, I will just, okay, now I will change the time also. Why I have to change the time? Because as I reduce the frequency, that will also change. So what I'll do is I will change this time period to maybe around, so this, I will change the timing here. This I will make it around another 0. I will add a 0 here. So now I'll run here. So what was the gain? 97. Let me see what is the peak to peak of this. I can see the gain. Can you see it is 1.92 divided by 20 millivolts. Can you see it's almost 96? The gain is still the same. So whether it is 5K or 50 kilohertz, gain is same. So let me make this frequency as something like, okay, 50 hertz. Let me make it 50 hertz and then change this time to, maybe I'll make this another 0. Let me again run. make it one more zero, make it one more zero, and then run now. Okay, that is because from 50 hertz that I made it too less. Okay, oh, sorry, this is, I just change it. Okay, let this be 20 micro, 20 micro. Sorry, this is 50 hertz. This is 20 micro. Sorry, that is amplitude 10 milli. This is 50 hertz. I have to change the timing here. Let me change the time to a few milliseconds. Let me make it 100 milli. Let me run. See, now I'm getting the output. Let me see what is the gain of the amplifier. If I see the gain of the amplifier, I'll keep one here, the other one I'll keep it here. Can you see the gain has reduced? You can see now. This is, how much is this? It is 124 milli divided by 20 milli. You see the gain has become 6.2. What is the time we are trying to do is, that we are trying to find is when the frequency of this input signal is 50k. Okay, let me write the frequency and gain. When the frequency is 50k, we had a gain of around 97. When we had it as 5k, this was 96, almost same. The moment I made it 50 hertz, the gain is 6.4 or 6.6 or 6.2. Can you see the gain has changed? Why the gain is changing? Because the frequency of your input signal changes. What is the meaning of this? That means this amplifier cannot amplify an AC signal of all frequencies with the same gain. When you see the gain is changed, that is what is known as frequency response of the amplifier. Let me write it as frequency response of amplifier. This amplifier has got some gain of kV for different frequencies starting from low frequency to high frequency. So when it was 50 kilohertz and 5 kilohertz, it is fine. So assume that this is 5k, this is 50k. It is gain of 96 or 97 was there. When it was 50 hertz, the gain is reduced. So if you do the same thing for maybe 500 kilohertz or 5 megahertz, the gain will further reduce. Meaning this gain doesn't remain constant for all frequencies. So how does this circuit responds for different frequency of the signal? It is nothing but frequency response of the amplifier. Typically, the frequency response of the amplifier looks like this. Can you see? It's changing. So at lower frequency gain is less. At mid-band frequency gain is almost constant, and it reduces if you go for very high frequencies. Typically, it will be like this. It increases, becomes constant, and then further reduces. So this is the frequency versus gain of the amplifier. Gain of the amplifier. So why this is important? This assume that you have designed an amplifier for around a gain of 50, 100, whatever the gain. Assume that you designed for 50. Now I need to find out between what frequencies this will give a gain of 50. You know that the gain is not 50 as the gain for all frequencies. Now we need to specify what are the frequency range over which the frequency gain is, or the gain of the amplifier is whatever intended. So we call it as FC1, FC2. FC1, FC2 are called as cut-off frequencies. Cut-off frequencies. If the frequency of the input signal is less than F1, are more than f1, the guaranteed gain is not 50, it will be less than 50. If it is between this and this, the gain is almost equal to 50, almost equal to 50. Now the question is, how did we come across this frequency fc1 and fc2? So what is, how did I mark this as point? Why not this point? Why not this point? Why not this point? So there is a reason for choosing these 2 points, fc1, fc2, as cutoff frequencies, where if the input signal lies between these 2 points, which is now called as bandwidth. Bandwidth. So what is the bandwidth of an amplifier? This is, let me write it as BA band width is nothing but fc2 minus fc1. The frequency should be well within this, the input signal, so that you will have to have a gain of sound. The question is, how did we locate this fc1, fc2? So now for that, so let us consider, so I hope all of you know what do you mean by, what is the relation between power and voltage? Power and voltage. Give me a minute. So we have this, so we know that power is given by, power is nothing but V into I. V into I. We also know that this is V square by R is the power. And we also know that this is equal to I square into R. Correct? So let us consider this relation. Let us consider this relation. Now let us take power, and this is V square by R. Sorry, V square by R. Correct. Next, let us assume that we have, let us, if the voltage, suppose if this is power P is equal to 1 watt, if resistance is equal to, assume that it is 1 ohm, then what is the voltage? So can I find what the voltage is? So now can I find the voltage as equal to, so what is this voltage? Is it not equal to under root of P into R? Correct? P and R will get multiplied. So this is it not 1 watt into 1 ohm? Is it not under root of 1, which is voltage is 1 volt? Voltage is 1 volt. So if power is of 1 watt for a resistance of 1 ohm, voltage is 1 volt. Now let us see, if the power becomes half watt, what is the voltage for the same R is equal to 1 ohm? So now let me make this as, I want to find what is the voltage for a half watt. Is it not half into 1? So what is this root of half? Sorry, root of 0.5 is 0.707. So when the power is 1 watt, the voltage is 1 volt. When the power becomes half watt, or the corresponding voltage, can you see it is 0.707 volt? So why we are trying to find this is, so assume that you have an amplifier having this type of frequency response. So now at this point I have a voltage of V1, and I will have a corresponding power of P1 over here, P1 over this image, okay, at this point. Now let me find out a point where there is a P1 by 2 power. So for this power to be half of this power, what will be the voltage? Can you see the voltage is V1 by, or V1 into 0.707? Because I know that if the power reduced by half, voltage will be 0.707 times V1. That's what we found here. So if the power becomes half, then the voltage is 0.707 times the voltage here. Correct? So now this point corresponds to power of half compared to this point. So this is one of my cutoff frequency. So you try to find the similar point here, where suppose if this is V, what is this V here? It is 0.707 V. So can you see these two are the points which is corresponding to FC1 and FC2. So this bandwidth, this bandwidth, is this bandwidth corresponding to half power points compared to this maximum power? So that's why this bandwidth is called as half power bandwidth. So how do you find FC1? FC1 is found at a point at a particular frequency where the voltage is 0.707 times the voltage at this point. So this is 0.707 times V1 here. This is V1. So this is how you find the bandwidth. So what is half power bandwidth? It is you identify a frequency where the output voltage is 0.707 times. So now we know that how do you find the gain? You find the gain by V1 by Vn. This by Vn. So can you see this becomes the gain of the amplifier? Can you see V1 is the output voltage and Vin is the gain. Vin is the input voltage. Output by input is gain. What is this? 0.707 times of V1 is the voltage at which power is half. So divided by Vin is this not the gain at half power point? Is this not the gain at half power point? Is this not the gain at maximum gain? So this is because the range over which we are going to find the bandwidth is called as mid band gain. Mid band gain. Whatever expression for AV we found it as minus HFE times RC by HIE is actually the mid band gain. Is actually the mid band gain. So where the half power bandwidth corresponds to 0.707 times V1. Suppose if you are specifying this gain in terms of dB, so if you are looking for gain in terms of dB in a frequency response, so then what is this? How do you get this point? Because we know that because dB is nothing but when you have V in V naught by V in is the gain. How do you represent in dBs? It is 20 log of V naught by V in is the gain in dBs. Correct? Now, what is this point corresponds to? Does this point corresponds to 0.707 times the gain? So then what is 20 log of 0.707? Is it not minus 3 dB? So this point, suppose if you have some x dBs at the maximum, at this point, at this particular frequency, that will be x minus 3 dB. X minus 3 dB. Suppose this is 40 dB here as the gain, here it will be 37 dBs. So because it is 3 dB down the maximum, so this corresponds to FC1, FC2. So where it is 3 dB down is FC1, FC2. So this is also called as 3 dB bandwidth. Half power bandwidth is same as 3 dB bandwidth. So why it is called as 3 dB? It is 3 dB down the maximum point. So this is 40 dB. Look for, instead of 0.707, look for where it is minus 3 dB if the graph y-axis is in dBs. If the graph of your y-axis is in dBs. So let me show you that over here. See, for this simulation, let me do frequency response. Let me just take out this. Now to do the frequency response, I will change this source from, okay, I will use this one. Okay, I will just make this now. I have removed the sine wave. So this is the source one. And let me do a frequency analysis. For doing the frequency analysis, I have to change this analysis setup. So this should be AC analysis. Now we can see this is the frequency response. Now if I run and see the output by input, can you see now this is the frequency response of the amplifier? Can you see this is frequency response? Can you see the gain is constant? Can you see the gain is reducing? Gain is reducing on either side. Now I can find the bandwidth. How do I find the bandwidth? Take You see the gain is 39.81 dBs. This is already in dBs. This is already in dBs. Now let me put one more cursor where it is 3 dB down the maximum. So this is 39.87. Make sure that this is at 36.8. So I'll make sure that this is at 36.8. You see now this is just have a look at the cursor one. Cursor one, is it now reducing? Can you see here? This is reducing. This is 36.8. Can you see it is 39.8? Can you see the difference is almost 2.9? Are you looking for this here? Okay, can you see it's almost 3 dB down? Can you see this is 3 dB less than 39? This is 39.81. Can you see it is 36.72, which is almost 3 dB down? So this corresponds to cutoff frequency. What is the cutoff frequency? It is 766 hertz. So now what is this FC1 is 766 hertz. The corresponding gain is, so let me write it here. I will write the frequency response, and so here it is 36.72 dB. Maximum gain is 39.8 dB, and this frequency is 766.2 hertz. Let me find the other frequency. Let me keep it on this side. So here also I have to go where it is 3 dB down. Am I just moving close to 3? Can you see this is almost close to 3 here? This is 3 dB. What is the cutoff frequency? Can you see it is 12 point? So here it is 12.13 megahertz. 12.13 megahertz. Meaning this here, this is in frequency, this is AV in dBs. So this is 39.8. Can you see this is 3 dB down line? So from here to it is 3 dB. So now this is 36, this is 39. You have a difference of 3 dB. This is FC1, one of the cutoff frequency. This is FC2, the other cutoff frequency. So this is your bandwidth, which is almost equal to 12.13 megahertz. If at all, if you want to amplify any signal, that frequency should be more than 766 hertz and should be less than 12.13 megahertz. It's because of this reason, when we actually used a 50 hertz signal, can you see the gain was hardly something like 6 instead of 97 in the earlier example. So now this is in dBs. Can you actually find what is the gain? So you know that if you have a gain of 97, so you can find this in dB. It is 20 log of 97. So what is 20 log of 97? 20 log of 97 is 39.73 dB. 39.73 dB is 97. Then what is 39.8 dB corresponds to? So this you can find as 10 to the power of 39.8 divided by 20. So what is this? 10 to the power of 39.8 divided by 20 will be how much? 97.7 is the gain. And what is this? 36.72 is 10 to the power of 36.72 by 20. Let me write it here. 37.7. Can you see it is 76.73 is the gain? Can you see this is that divided by 0.707? Can you see it's is this almost 0.707 times the maximum? So this is when it is 3 dB down, this is almost equal to 0.707 times this one. So what is 97.7 into 0.707 is almost equal to 6970. So there is some small error. Otherwise, this is what is the gain. This is maximum gain. This is the gain at the bandwidth. If the frequency is less than this, the gain reduces. If the frequency is more than 12.13, gain again reduces. So what is bandwidth now? Bandwidth is the frequency between which the power is more than half of the power. If the power is less than half of power, then that is not a bandwidth frequency. So that is not a frequency where your gain will be expected. Gain will be expected. So why we are making these 3 dBs? Because in electronics we have to demarcate some point where the frequency is said to be cutoff frequency. So we consider half power point as a cutoff point. So if the power is less than half, we treat it as that's not a good signal. So that's why it is also known as half power bandwidth. Half power bandwidth. So we looked into input impedance, output impedance, and bandwidth of the amplifier. So these are the two important parameters. For a good amplifier, this is one bandwidth which we got it as 93.13. Suppose if the bandwidth of the amplifier is something like this is good. So if the bandwidth is more and more, it is better and better for an amplifier. And of course, even this should be as small as possible. Even if it is zero, that is the best one. So in the previous case, we saw a good amplifier should have large R in, less R out, and the bandwidth should be more. Should be more. So if the bandwidth is more, it's a good amplifier. These are the three parameters of an amplifier. So while finding the bandwidth, we try to identify where it is half power bandwidth, which is nothing but 0.707 times the voltage at the maximum point. So which is nothing but 3 dB if you measure in terms of dBs. So that's why we got it here. That's why we got it as 3 dB down here. Correct? Of course, why this reduces on either side? Of course, a different analysis. So for which we should know what is the filter response of the circuits. So which is bit out of scope of this particular course. The detailed one is there in other videos. You can have a look at it. Thank you.